We are going back to limits. And since we're going back to limits, it's important to just kind of remember what are some of our key limits. So the first one in blue here, if we're dividing by infinity to any power from either side, from negative infinity or positive infinity, basically we're going to get 0. If we're dividing by 0 from the positive side, if we have 1 over x from the positive side of 0, we get positive infinity. We get 1 over x from the negative side, we get negative infinity. And again, these are some key limits. So we want to remember these limits. These are very important. But there are lots of limits that we cannot work out. Okay, and this one here, although we could actually do sine x over x as an identity, we can't actually do it algebraically. Okay, same with this x to the power x. We can't actually do this algebraically either. Okay, so although we do know this one, we want to know this one as an identity. We can actually, this method that we're going to do is going to be able to deal with these ones now all algebraically. Okay, so we're going to use a rule called L'Hopital's rule. Okay, and the L'Hopital's rule is for indeterminate forms. And it's basically any time we run into infinity over infinity or 0 over 0. And there are some other forms that are also considered indeterminate forms, such as infinity minus infinity, infinity times 0. We don't know what those could be. Those could be anything. Infinity times 0 can be anything. Infinity minus infinity can be infinity, 0, or 15. We don't know. Same with infinity to the power of 0, 1 to the power of infinity, and 0 to the power of 0. Now, these are all indeterminate forms, just like infinity over infinity, but we can't do limits on them until we put them into a ratio. So all these purple ones must be converted into either infinity over infinity or 0 over 0. And then we can use this rule. So basically what L'Hopital's rule is that we apply the derivative to the top and to the bottom independently. We don't use quotient rule. We differentiate the top and we differentiate the bottom. Now, we can only do this if we have the condition of infinity over infinity or 0 over 0. So, in this case here, we always check first. So when I check my limit, when I plug in my 0, I get e to the power of 0, which is 1 minus 1, over x, which is 0, and I get that 0 over 0. That's key. That 0 over 0 is key because if anytime I encounter that in a limit, I can apply L'Hopital's rule. And L'Hopital's rule is this. Once we have that condition, okay, L'Hopital's rule, I'm just going to write L'Hopital's here. The way it works is we just do another limit and we differentiate the numerator. So e to the 2x times 2 minus the derivative of 1, which is 0. We differentiate the numerator. So notice I differentiated the numerator and I stopped. Okay, I'm not going to do quotient rule, so that's my derivative of the numerator. And then I differentiate the denominator, and I do that separately from the numerator. The derivative of the denominator is 1. So what this does is gives me another form that I can use. Okay, in this form, I can check the limit of this, and the limit of this new form will equal the limit of the original form. So that if I check the ratio of the derivatives, it will equal the limit of the original form. So now I can just plug in. So I'm just going to plug in 0. So I get 2 to the e to the power 2 times 0, which is 0, over 1. So the limit is equal to 2. So now I can make the statement. Well, although my original limit didn't work, when I applied L'Hopital's rule and got a result, that limit now is the limit of the original one. So as x equals 0, e to the 2x minus 1 over x, the limit of that expression is equal to 2. And we can check this on our graph. Okay, and it's always good to check our answers on Desmos.